So in this video, we're going to apply the extreme value theorem in the context of a quartic polynomial. The quartic is just a fourth degree polynomial. So when we're using the extreme value minimum, the things to remember are we're looking for the global minimum and global maximum outputs of a function over a closed interval. So with the extreme value theorem, we always are going to be working with a closed interval. So in this case, I've defined the quartic polynomial 3x to the fourth minus 4x cubed over the closed interval from -1 to 2. And we want to find the extreme values, the largest output and the smallest output of the function over that closed interval. As in the previous video, my suggestion is always to graph the function over the closed interval in which you're interested, and then visually identify the global minimum and the global maximum so that you know what you're looking for. It gives you an answer key for when you're doing your calculus and your algebra. If you make a mistake and it doesn't match up with what you're seeing in your graph, you'll know that you need to redo things. So there's a 4-step process that we used in the previous video. The first 3 steps are kind of the nuts and bolts, because step 4 was just to analyze the results. So the first step is find your critical numbers. Where are the places where the function has its high and its low points on that closed interval? And remember, that's going to occur when the derivative is equal to 0. We're going to look for places where we have horizontal tangent lines. We're looking for locations of relative minima and relative maxima. So step 1, find your critical numbers. So critical numbers. And to do that, we take our function, and then we just take its derivative, because the derivative tells us the slopes of the tangent lines of the function. So we get a 12x cubed minus 12x squared right there for the derivative. And then we want to ask, is this derivative undefined any place? And it isn't. It's a third degree polynomial. So the domain of it is from -infinity to infinity. So we don't need to worry about places where the derivative is undefined. And so now we just need to find the locations of those horizontal tangent lines. So to do that, we take the derivative and we set the derivative equal to 0. And if we look at this, we'll see that we can factor it as 12x squared times x minus 1 should be equal to 0. And then using the zero product property, that tells us that 12x squared equals 0, or x minus 1 equals 0. So we can see from here that x will be equal to 0. And then we see that x equals 0 is a repeated root. Sorry, x equals 1. That's horrible algebra there. Add 1 to both sides isn't going to give you a 0 right here. X minus 1 equals 0 when x equals 1. So either x equals 0 or x equals 1. Those are our critical numbers. Step 2 is evaluate your function at those critical numbers. So we want to evaluate f of 0. So we're just plugging 0 into the original function. So we get 3 times 0 to the fourth minus 4 times 0 to the third, which is just going to equal 0. So f of 0 equals 0 is important to us. And then the other critical number is 1. So we're going to go f of 1 equals 3 times 1 to the fourth minus 4 times 1 cubed is just going to be 3 minus 4 is equal to -1. So we get f of 1 equaling -1. And then the next step in finding the extreme values, or the max and min outputs of the function on a closed interval, is to evaluate the function at the endpoints if the endpoints of the closed interval aren't themselves critical numbers. In this case, neither -1 nor 2 was a critical number of the function, so we need to evaluate the function in step 3 at the endpoints of the closed interval. So we need to evaluate f of -1, so we're going to get 3 times -1 to the fourth power minus 4 times -1 cubed is going to be equal to 3 plus 4 is 7. So we are interested in input -1, output 7. And then the other endpoint of our closed interval is 2. So we're interested in calculating f of 2, which is going to equal 3 times 2 to the 4th power minus 4 times 2 cubed, which is going to be 3 times 16 minus 4 times 8, which is just going to equal 8 times 3 times 2 minus 4, which is going to be 8 times 6 minus 4 is 2, which is going to be equal to 16. So we're interested in f of 2 equaling 16. And notice I can look at these outputs and then step over to my graph and check, hey, does it look like I made an arithmetic error or not? In this case, it looks like I'm okay. And then step 4 of the process of finding the extreme values or the extreme outputs is just to look through the list of outputs you have and say, which is the smallest? There's your absolute minimum on that closed interval. Which is the largest? That's your absolute maximum on that interval. And then you draw a conclusion. The absolute maximum is 16 at, it's located at input 2, output 16, and the absolute minimum is -1 at the point -1, -1.